Okay, so you're ready.
Okay, yeah. Thank you very much, Migo, for the kind introduction. And it's a great pleasure to give the seminar here. Thank you for having me. So today I'm going to discuss my work on the application of open quantum systems for Quarkonia and to describe its production in heavy ion collisions. Here is the content on my talk. So I will start with a brief introduction of the physics in heavy ion collisions, like why we are doing heavy ion collisions, and the idea is to search and study the properties of the quark-gluon plasma. And to study the properties of the quark-gluon plasma, we need to use different probes of the quark-gluon plasma, and the heavy quarks or the heavy quark bound states, i.e. Quarkonia, is an excellent hard probe of QGP, which I will explain later. And then I will introduce the framework of open quantum systems to describe heavy quarks and quarkonium inside the quark-gluon plasma, which we also need to use effective field theories to simplify the description of heavy quarks and quarkonium. And then I will show you how to derive the Lindblad equations under certain approximations. And I will also discuss the connection between the Lindblad equations and the semi-classical transport equations like Boltzmann equations or Langevin equations that a lot of groups were using. And then I'll kind of switch the topics to discuss how to use quantum computers to simulate the time evolution of open quantum systems. So far, the quantum computers is at its baby stage, so we cannot use it yet to simulate heavy quarks in quark-gluon plasma. But I will discuss two very simple examples. The first one is a two-level quantum system. And we can think of this two-level system as bound and unbound states. And then I will discuss a slightly more complicated theory, which is a U1 gauge theory in 1+1 dimension, also known as the Schwinger model. Okay, so heavy ion collisions and the quark-gluon plasma. We know the quantum chromodynamics has a property of asymptotic freedom, which means at very high energy scales, the coupling between quarks and gluons becomes weak. So naively, we would expect that at a sufficiently high temperature or high density, the energy scale is high. So the QCD matter under that high temperature or density condition will become the confined phase, where the quarks and gluons are freely moving. And we call that phase of the QCD matter the quark-gluon plasma. So to search for the existence of the quark-gluon plasma and study its properties, we build up heavy ion collision experiments at both the relativistic heavy ion collider in New York and the Large Hadron Collider in Europe. And in these collisions, we accelerate heavy nucleus like gold or lead to very high velocity and then let them smash. And in this cartoon, we have two nuclei at some impact parameter B. And after the collision, there are a chunk of stuff produced in the middle. And we try to study the final state particle distributions and infer if there is a quark-gluon plasma produced. And if there is a quark-gluon plasma produced, what the properties of the quark-gluon plasma matter for the final state particle distribution. And here is a phase diagram plot showing kind of what a range of the phase diagram are we probing right now. Like at LHC, which is very high energy, we are probing the phase diagram that is very close to zero chemical potential. And the phase transition here we have known is a smooth crossover. But right now the RIC is doing a beam energy scan and trying to look for the critical point of the quark-gluon plasma, and which is the endpoint of a first order phase transition. So it's the endpoint of the first order transition, and on the left, it's smooth crossover. And right now, these experiments are still undergoing. And from the past decade, what we have learned that indeed we created a quark-gluon plasma in the laboratory, but the quark-gluon plasma we created is a strongly coupled medium instead of a weakly coupled quarks and gluons. And its lifetime is about 10 Fermi overseeing the lab frame, and the temperature currently achieved is from 150 to 600 MeV. And to study the properties of the quark-gluon plasma, we need to look at some final state particles. You can look at pions, protons, or kaons, but those particles are called light probes because they have a very small mass. And most of the time, people look at the collective motion of those light particles. But in addition to those pions and the protons, we also have hard probes of the quark-gluon plasma, which involves a very large energy scale, such as the mass of the heavy quarks or the energy of a jet. And since these kind of probes involve a large energy scale, they were produced early in the collisions, and then they go through the quark-gluon plasma phase, and we can look at how the production of these particles are modified in heavy ion collisions compared to that in proton-proton collisions, and then infer some properties of the quark-gluon plasma. So now let me go to a little more details about Quarkonia as a probe of the quark-gluon plasma. So the idea can be dated back to the early studies of plasma screening effect on heavy quark bound states. So we know the Quarkonium it can be thought of as a non-relativistic bound state of a heavy quark and a heavy antiquark. So the properties of the ground and the lower excited states in the Quarkonia spectrum can be well described by the Schwinger equation with some potential models. A famous potential model is called Cornell potential. It has a short-range Coulomb repulsion and a long-range linear rising confining potential. And in vacuum, you just take this potential and solve the Schrödinger equations to find the eigenenergies of each state, and then you can compare that with experimental measurements on the spectrum of Quarkonium. But when we put these QQ bar bound states inside the quark-gluon plasma, there is a plasma screening effect, which will suppress the color attraction between the Q and the Q bar. For example, here, I'm just assuming the linear rising part is completely screened, and the short range of the Coulomb potential becomes a Yukawa type, like the MD here is a Debye mass. And then you would expect that at sufficiently high temperature, the screening is very strong, and the potential becomes too weak to support the formation of bound state. Mathematically, that means if you solve your Schrödinger equations, you just find no solutions for bound state. And that corresponds to the melting of a specific Quarkonia state. And then if there is a quark-gluon plasma produced in heavy ion collisions, we would expect the production of Quarkonia to be suppressed due to the plasma screening effect. And the measurement of the suppression can tell us about the temperatures of the quark-gluon plasma. This static screening picture was confirmed by many lattice calculations. For example, in this plot, I show you the singlet free energy as a function of temperature and distance. And the black curve here, you can think of that as the vacuum potential, the Cornell potential. You see clearly the linear rising part. But as we increase the temperatures of the plasma, you can see the screening part becomes flattened, right? And the position it starts to become flattened, becomes smaller and smaller as we increase the temperatures. This indeed tells us, yes, the color attraction between the heavy quark pair is suppressed inside the plasma. And since different Quarkonia states have different sizes, like some deeply bound states live here, some shallow bound states live here, they will be modified by the screening differently. And as a result, they will have different melting temperatures. For example, the most deeply bound state, upsilon 1s, has the highest melting temperature, while some shallow bound states like the psi prime 2s has a very small melting temperature. And then you can imagine the collection of all Quarkonia states can be thought of as the thermometer of the quark-gluon plasma. If you measure the suppression of each Quarkonia state, you can try to learn more about the temperature of the quark-gluon plasma. This simple Debye screening picture works. It has a very good physical intuition, but in practice, it is not enough to describe the experimental data, because in addition to the Debye screening, there are also dynamical processes happening inside the quark-gluon plasma, and they are called dissociation and recombination or regeneration of Quarkonia states. So let me explain these ideas. So assume we have some potential here in the black line, and we solve our Schrödinger equations, we get a bound state, right? This blue curve here describes the wave function of the bound states. So we have a bound state here. And at any time inside the quark-gluon plasma, there could be thermal fluctuations, and there could be enough amount of energy, delta E, transferred from the quark-gluon plasma to excite the bound state to continue. So instead of a bound state wave function, now we have a scattering wave. And this process is called the dissociation of the quark-gluon plasma. It can happen even if the screening, is weak, right? You still have a well-defined bound state. So in other words, this dissociation can happen even the temperature of the plasma is below the melting temperature of the quarkonia. And the inverse process of this is the recombination. Like we start with the scattering wave and unbound QQ bar there. And at any time, they can radiate out enough amount of energy to the environment. And by doing that, their energy falls down and they can form a bound state here. And this process is called recombination. And they kind of are just like the inverse process of each other. And for the consistency of the theory, you need to have both in your description of Quarkonia. And from a phenomenological side, it has also been shown that the recombination is very important to describe the Harmonian data. So here is the idea. Like here, I show you 3 measurements at different collision energies. The black dots are from the 200 GeV Phoenix measurements at RIC, and the blue one is from ALICE at 2.76 TeV, and the red dots are from the ALICE again at 5 TeV. As you can see from this plot, as we increase the collision energies, the G psi is actually less suppressed. But this is very kind of counterintuitive, because naively we would expect that as we increase the collision energies, the quark-gluon plasma produced is hotter. It has a higher temperatures, so the screening will be stronger. And then we naively would expect the G psi to be more suppressed as we increase the collision energies. But we just observe the opposite. As we increase the collision energies, the G psi is less suppressed. And the reason is because they enhanced recombination from open heavy quarks when we increase the collision energy. So the logic is, as we increase the collision energies, there are more charm and anti-charm quarks produced inside the fireball. And at the freeze out, like the density of the CC bar is much higher than at lower temperatures. And the chance for a charm quark to recombine with another anti-charm quark is much higher. And this enhancement of recombination wins or dominates over the enhanced dissociation. And this is why we see an enhancement, or we see the G psi is less suppressed. But many phenomenological models, they use classical transport equations. And in that approach, it's very difficult to put dissociation and recombination in the same theoretical framework. And people just use different models for the recombination. And that introduces some kind of systematic uncertainties in the description of the recombination. So what we want here is a consistent description of these 3 effects: screening, dissociation, and recombination. And as I will argue in the following, to have a consistent picture or consistent description, we need to go beyond the semi-classical approach and using some more quantum approach. And this is really the motivation for us to use open quantum system to describe heavy quarks. And I will come back to this issue after I introduce the concept of open quantum systems. So here is a kind of brief introduction of the open quantum system framework. So it is very general. Like you can think of, you have some quantum systems. It has 2 parts, a subsystem part and an environment part. Like for us, the subsystem would be just like heavy quarks and heavy antiquarks, and the environment is the quark-gluon plasma. And we are doing kind of Hamiltonian dynamics. We are doing real-time evolution. So we will use the Hamiltonian to describe the time evolution. And the Hamiltonian has a part, HS, describing the subsystem, a part that describes the environment, HE, and a part that describes the interaction between the system and the environment, HI. And we assume in the beginning the density matrix is factorized. Like the density matrix involves the subsystem part and environment part, like our heavy quarks and the quark-gluon plasma. And if we look at the time evolution of the whole system, they evolve according to some unitary evolution operators. And this unitary evolution is time reversible because QCD without the theta term is time reversible. But our interest is in heavy quarks or in the system. So we can trace out the environment degrees of freedom. And when we do that, we obtain a reduced time evolution equation for the subsystem density matrix or for the density matrix of the heavy quarks. And symbolically, this equation can be written in this way. So you just start with the total density matrix, you involve it according to the U and the U dagger, and then you trace out the environment degrees of freedom. And symbolically, this reduced evolution is written this way, and one can show that this reduced evolution is non-unitary and time irreversible, even if we start with a theory that is time reversible. But this kind of symbolic expression is too abstract to work or to use in practice. So in practice, we need to simplify this expression and obtain some well-defined differential equations for the subsystem density matrix. And that is what I'm going to do in the next. So here we use weak coupling assumption, but we only require a weak coupling between the subsystem and environment. In other words, we only require the HI is a weak interaction. The HS and the HE themselves can be strongly coupled systems. And then we can expand the unitary evolution operator in the old-fashioned time order perturbation theory. And then we can trace out the environment degrees of freedom explicitly in the equation. And after we do these steps, we obtain a finite difference equation. And it's written down here. It's not yet a well-defined differential equation. It's just a finite difference equation. So we start with some density matrix at 0, and we evolve it to a time step t. And this is the kind of evolution of this density matrix. And let me try to use this picture to explain the structure of these equations here. So remember, like in the time evolution of the density matrix, we have a U operator on the left and a U dagger operator on the right. So that is represented by the solid lines with arrows here. So a U on the left and a U dagger on the right. And when we do weak coupling expansion at the second order, we can have 3 possibilities. You can take 2 operators from the U on the left or 2 operators from the U dagger on the right. Or you take 1 operator on the left and 1 operator on the right. And that is represented by this cross diagram here. And for the 2 diagrams in the first row, you can further decompose it into the real part and the imaginary part. And this sigma AB, L, AB here represents the real part of these diagrams. And it can be thought of as a correction to the Hamiltonian of the subsystem. And this part here includes the Debye screening that we talked about before. And the imaginary part of these 2 diagrams will show up in this term here. Like it has this structure, L dagger L, and times some coefficient gamma ABCD. And these terms here will represent the dissociation of the Quarkonia state. Or in other words, you can think of this as an imaginary potential, which accounts for damping of the state. And finally, which is the most important part for recombination, is this cross diagram. And it's represented by this L rho S L dagger, like this, each attachment can be thought of as L here. And this diagram will correspond to recombination process. And the reason why it is difficult in the beginning to write down a good description of recombination is because people neglect this diagram. They talk about real potential, imaginary potential, which are only coming from the first 2 diagrams. It is important to include the 3rd diagram to have a consistent picture of Quarkonia dynamics. And here are the terms in these Lindblad or pre-Lindblad equations. For example, the gamma ABCD is defined by some transitions in the subsystem states, like you have states A, B, C, D, and they are connected by some system operators OS, which is coming from the interaction part. And we also have a kind of correlator or Green's function here. And this Green function is defined as the Whiteman correlator of the environment operators, which I will come back in greater detail later. And this sigma AB term is similar to the gamma ABCD, but it includes a sign function here. And it is a sign function that splits these two diagrams into the real and imaginary parts. Okay, so this is a heavy slide, but it's better to come back to some physics now. Like, as I emphasized, this is only a finite difference equation yet. It's not a well-defined differential equation. So we're looking for some simple limits where this equation can be converted into a well-defined differential equation for the system density matrix. And that can be achieved in two limits. And one limit is called the quantum optical limit, which is valid at low temperature. And the other limit is called the quantum Brownian motion limit, which is valid at high temperature. In either limits, we assume the interaction between subsystem and environment is weak. So one can do a Markovian approximation. And once we make these approximations, one can write down a Lindblad equations in each case. And the Lindblad equations can be formally encoded in this way. So now we have a well-defined differential equation for the subsystem density matrix. And these Ln operators are called Lindblad operators. And depending on your kind of theory describing Quarkonia, the form of these Lindblad operators can be different, but there are general procedures to write them down. And also this system Hamiltonian part becomes an effective system Hamiltonian because it gets some correction from the thermal effect. This Lindblad equations is a quantum master equation, and we can further connect these quantum evolutions with the semi-classical transport equations. And one way to see that is to use the Wigner transform, which is defined in this way. So we have some quantum density matrix describing the state. By taking some off-diagonal elements of the density matrix and applying a Fourier transform, we can connect this quantum state or quantum probability with the classical probabilities. This is a phase-space distribution in position x and the momentum k. But this Wigner transform does not guarantee positive definiteness. So one also needs to do some smearing for positivity of the phase-space distribution. And then one can just apply this Wigner transform to these Lindblad equations and perform a further approximation called gradient expansion, which corresponds to H bar expansion. And by taking the leading order terms in that H bar expansion, one can arrive at the semi-classical transport equations. For example, for Quarkonia, in this open quantum optical limit, we can obtain the Boltzmann equations, while in the quantum Brownian motion limit, we will arrive at the Langevin equations, which is equivalent to a Fock-Planck equation. And let me give you more intuitive ideas of these two limits. Like, as I said, the quantum optical limit is valid at low temperature, while the quantum Brownian motion is valid at high temperature. So whether we take one limit or the other depends on a hierarchy of timescales. There are three relevant timescales involved in the problem, like tau e, called environment correlation time. And that can be read from the environment Green's functions. Like I take this Whiteman Green's functions. There are two environment operators, and the density matrix is taken to be a thermal state. And one can, just based on a simple scale argument or energy scale argument, we would expect that the environment correlation time is given by 1 over the temperature, because the temperature appears as a scale in these correlators. And for the subsystem part, we have a subsystem intrinsic time scale. And this one is given by the inverse of the typical energy gap in the system. So like naively, you can think of this gives the time scale for the QQ bar revolving around each other, but they involve some transitions. So it's given by the energy gap. Like when you go from one state to the other, you take the energy difference and you inverse that. That gives you kind of an intrinsic time scale for that process. And finally, it's a relaxation time for the subsystem. So we know Quarkonia or any system in the plasma will gradually approach thermal equilibrium. And that process can be described by a relaxation process, and this time scale is for that relaxation process. It depends on the coupling between the subsystem and the environment. You can imagine if the subsystem and environment are extremely weakly coupled, then this tau R will be very large, much bigger than the other two time scales. And that is what happened in this hierarchy of time scales. We assume the environment, we assume the relaxation time is much bigger than the environment correlation time in both limits. And this is valid in the weak coupling limit where tau R kind of diverges. But in the quantum optical limit, we assume the relaxation time is much bigger than the subsystem intrinsic time scale, while in the quantum Brownian motion limit, we assume the subsystem intrinsic time scale is much bigger than environment correlation time. So what are the kind of physical picture corresponding to these two hierarchies? So when this happens, you can imagine during the dissociation or recombination of Quarkonia states, your Quarkonia state have stayed there for a while. They're just revolving around each other for many periods. And this tells us that the QQ bar bound state is a good basis for the calculation. Like when the temperature of the quark-gluon plasma is low, the quark-gluon plasma cannot see the internal structure of the QQ bar. The QQ bar kind of stays as a well-defined bound state for a relatively long time period during the dynamical process. So which means a good basis for calculation in this case is just the bound state and unbound state. And then the dynamics of Quarkonia is basically transitions between bound and unbound state. And the transition between bound states is also possible, but it's suppressed when the size of the Quarkonia is small. But in the quantum Brownian motion limit, it's different from this one. In this case, we have a very high temperature quark-gluon plasma such that this condition is valid. And then the resolving power of the quark-gluon plasma is very strong. The quark-gluon plasma can see individual heavy quarks inside the bound state and interact with them more independently. And in this case, instead of have well-defined transitions between states, we now have some kind of jiggling dynamics of the heavy quarks inside the bound state. So it is more like diffusions of the heavy quark pairs inside the bound state. Instead of responding to the QGP as a single object, they would like to respond more individually. And in this case, the Quarkonia dissociation happens because of this wave function decoherence. Like you can have a well-defined wave function to begin with, but this jiggling around dynamics just kind of distort that wave function, and that leads to the dissociation of Quarkonia state. And the same thing can explain recombination. Like you can start with a state that has zero overlap with the Quarkonia state, but due to this diffusion of heavy quarks, that wave function, which is originally orthogonal to a bound state wave function, can develop some overlap with the bound state wave function. So these dynamics can explain both dissociation and recombination. Okay, now I want to give you more concrete examples of Lindblad equations corresponding to each limit. And for that, we need a kind of field theory or some theory, quantum theory to describe heavy quarks inside the quark-gluon plasma. And the one I'm going to use is non-relativistic effective field theories. It's well established for Quarkonia studies in vacuum. In vacuum, we have three widely separated scales, like the heavy quark mass, the typical relative momentum inside the bound state, and the typical binding energy of the bound state. Like for Charmonia, the V squared is about 0.3, and for Baltimonia, the V squared is about 0.1. So V here is a typical velocity between the heavy quark pair inside the bound state. And since the system is non-relativistic due to the heavy quark mass, we have a well-defined hierarchy of energy scales. And then one can derive some effective field series by integrating out some energy scales. For example, if we start with QCD and integrate out the hard scales above the heavy quark mass, then one arrive at the non-relativistic QCD or the heavy quark effective theory. But there's another scale called soft scale, MV. If one further integrates out the soft scales, then one would arrive at the potential non-relativistic QCD, which has been widely used for Quarkonia dynamics. And then you arrive at a theory describing the ultra-soft dynamics. This is a story in vacuum and is well established. But once we put the QQ bar of the Quarkonia inside the quark-gluon plasma, there is another energy scale, which is the temperature of the quark-gluon plasma. And depending on where temperature fits in this hierarchy of energy scales, we may arrive at different descriptions for the Quarkonia inside the quark-gluon plasma. And in the following, I will describe two situations where we have a well-defined hierarchy of scales involving the temperature. So the first one is a high temperature limit. And by high temperature, I mean the temperature fits between the mass and the relative momentum mv. And in this case, we are using kind of non-relativistic QCD to describe the heavy quark dynamics. And this is the Hamiltonian motivated from NRQCD. So we have some kinetic terms for the heavy quarks. Each heavy quark and a heavy antiquark have some light degrees of freedom and a gauge field. And then the interaction between the heavy quarks and the environment is done in this kind of A0 interaction or Coulomb interaction. The A0 is from the environment, the gauge degrees of freedom. And then the coupling with the heavy quark is happening at a specific position. And the interaction with the anti-heavy quark happens at a different position, but with the opposite sign due to the different color charges. And then one can just use the procedures I described earlier to weak coupling expansion, obtain the Lindblad equations in the quantum Brownian motion limit. And this is the Lindblad equations corresponding to this case. And we have some operators here. They're called Lindblad operators. And in this case, Lindblad operators is written here. It involves a part that accounts for the interaction with the heavy quark and a part accounts for the interaction with the anti-heavy quark. And they have different color charges. And you can also see there's a term that is suppressed by 1 over mt here. And this is coming from a next leading order expansion in the quantum Brownian motion limit. And it kind of accounts for dissipation effects in the dynamics. So if you want to have your Quarkonia system to summarize properly in the end, you have to include these terms. Otherwise, you just get some non-thermal distributions in the end. And this is called dissipation terms. And it has been studied in the literature and shows these dissipation terms can kind of delay or suppress the Quarkonia suppression. So it has some big effect phenomenologically also. And if we look at the Lindblad equations again, another point that I want to emphasize is this environment correlators here. This D is defined by just like two A0 terms, and you take the trace over the environment density matrix. This is just a Weidmann function in the sum of field theory. But it is important to notice that it is a zero frequency of this correlator that contributes in the quantum Brownian motion limit. And this point will be different in the other limit that I'm going to describe later. So it's a zero frequency here. And this one would correspond to the heavy quark diffusion coefficient. People have derived these Lindblad equations, and there has been many studies on this. And solving these Lindblad equations in 3D is expensive, but doable. Like in the recent paper by Nora, Miguel, Mike, Antonio, and Peter, and Johannes, they solved this in 3D, and they did some phenomenological studies and agrees with the data very well. But now I'm going to describe the other limit where the temperature corresponds to low temperature. And by low temperature, I mean the temperature is on the order of below the binding energies. So this would correspond to the later stage in the heavy ion dynamics when freeze out happens. And in this case, one can derive the P-inner QCD by integrating out the scale MV without worrying about the temperature scale because the temperature is far below the scale MV. And then one arrive at the potential non-relativistic QCD. The degrees of freedom are QQ bar color simplet labeled by S and the QQ bar color octet labeled by O. And the kind of free theories of the color singlet and octet are just Schrodinger equations with some potentials. And since the potential for color singlet is attractive, so and the potential for color octet is repulsive, so we only have bound state in the color singlet channel. Any color octet state in this theory so far is an unbound state. So the bound and unbound transition that we're interested corresponds to a singlet and octet transition in this Lagrangian. And then we can just look at the interaction part for the color singlet and the color octet. And in this theory, it is corresponds to a dipole interaction, which is obtained from a multiple expansion. Like the size of the Quarkonia here, R, is typically given by 1/mv. And we also have a gauge, a chromoelectric gauge field here that couples the environment and the QQ bar system. And when the Quarkonia is almost at a rest in the quark-gluon plasma, we would expect that the R times T scales as V using our hierarchy of energy scales. And since V is a small number in the non-relativistic setup, this interaction is suppressed. And that explains the weak coupling expansion that we used to derive the Lindblad equations. And it is a weak coupling because the size of the Quarkonia is small rather than the coupling constant is small. This is different from the high temperature case. And then one can derive the Lindblad equations by taking this interaction vertex and work out all terms that are leading order in the velocity expansion and sum over all interactions that are not suppressed. And what I mean by this interaction is not suppressed, it is this interaction here. Because this is a covariant derivative, it has an A0 coupling for the octet field. And this term is not suppressed by any powers of V. And we need to sum these interactions to all orders if we want to do a kind of power counting in velocity rather than coupling constant. And this is what we arrived. So I first derived these equations with Thomas Mee in these two papers. As I explained earlier, this is a Lindblad equations or finite difference equation. This term corresponds to static screening. And using the procedures, we showed that this term gives us recombination in the Boltzmann equations, while this term here gives us dissociation of Quarkonia in the Boltzmann equations. And here I just write out these two collision terms for the Boltzmann equation. They're fully derived from the PNR-QCD Lagrangian. You can recognize some like dipole transitions between bound state wave function and unbound state wave function. And similarly for the recombination term, we also have some energy momentum conservation terms that describes the conservation in the dissociation and recombination. We also have some phase space integrals just for a typical Reed's calculation. And finally, I want to emphasize these two terms depend on different environment correlators, and which I call G++ for dissociation and G-, for recombination. And the reason why I call it plus or minus will be manifest in the next slide. But here I just want to emphasize in the dissociation and recombination terms, we have different environment correlators showing up. And here are these two environment correlators, like it's called G++ and the G-. The G++, we have two electric fields. They are just from the interaction vertex in the PNR-QCD. And since we sum over the A0 terms with the octet field, we have Wilson lines connecting these two electric fields to some points at infinite time. And then these 2 points at infinite time are connected to the same point spatially. While for the G-, in recombination, these two electric fields are connected to the past infinite time and then connected to the same spatial point. And the reason why the Wilson line kind of orientation is different between these two cases is because in dissociation, we have a color singlet state to begin with. There is no A0 interaction in the beginning. And the Wilson lines pointing to plus infinity accounts for final state interactions after the dissociation. So after dissociation, the color singlet becomes color octet, and then that A0 interaction started. While for recombination, the final state is a color singlet state. There's no interaction in the final state, but we start with a color octet state. So these Wilson lines account for the initial state interactions between the color octet and the quark-gluon plasma. And for the system to summarize properly, we need to maintain a Kubu-Martin-Schwinger relation or KMS relation between these two correlators. Otherwise, your system will not summarize properly. And one can show that if the environment density matrix is invariant on the parity and the time reversal transformations, then you can show that under PT transformations, these two correlators correspond to each other and they satisfy the KMS relations. And in the end, if we only interested in the total yield of Quarkonian states rather than differential distributions, then we integrate over all momentum states. And for that, equivalently, we are setting the positions of these two electric fields to be the same. So R1 equals R2. And when that happens, you basically just have two electric fields and a joint Wilson line connecting them. There is no infinity involved anymore. Only in differential processes, you need these Wilson lines at a plus or minus infinite time. And this correlator has some similarities with another correlator that has been studied a lot in the heavy ion community. That is called the heavy quark diffusion coefficient. That one is defined by these Wilson line configurations. Again, we have two electric fields, but these two electric fields are connected to both plus infinity time and negative infinity time by Wilson lines in the fundamental representation. So this one has been studied a lot. You have Wilson lines coming from negative infinite time to positive infinite time. And this is closely related to the heavy quark dynamics because for a heavy quark, it's open. It carries color all the way from the beginning to the end. So it's a colored object throughout. That's why you need Wilson lines and in the fundamental representation to account for its interaction with the quark-gluon plasma. While in our case for Quarkonia, since we have a color octet state either in the beginning or in the end, the Wilson line kind of only go in one direction in time, either plus infinity or negative infinity. And since the color octet pair is kind of in the adjoint representation, the Wilson lines here are in the adjoint representation. And you would think these two correlators are very close to each other. They may just have same values if we calculate them. And we, in a recent paper, we did a calculation about this correlator at exact next to leading order. We show that the temperature dependent parts between these two correlators agree. Like they have the same temperature dependent parts at next leading order, but the vacuum parts differ by a constant. Like in the heavy quark case, people have calculated by Mikko Lai and his collaborators, and they found a negative 2/3 pi squared here. While in our case, we calculate this one and the vacuum part has a positive 1/3 pi squared here. And we also checked this 1/3 pi squared term with this paper, which is only a vacuum calculation. And we found an agreement about this constant with this paper. So these calculations kind of demonstrate that these two correlators are indeed different objects because they have different finite pieces at next leading order. And you would expect that at next leading order, this finite constant in the vacuum piece may lead to difference in the finite temperature part. But this immediately introduces another puzzle because if you think about these two correlators in the temporal axial gauge, where the Wilson line becomes trivially identity, you just have two electric fields there. Like, how can you explain the difference between these two correlators in the axial gauge? And this, I don't know the answer. It's open now. Okay, how much time do I have? Yeah, I think I described all I want to say about open quantum system for Quarkonia. And now I want to kind of change the topic a little bit and talk about quantum simulations for the open quantum systems. And I think I should be quick about this section. So the one thing is the quantum circuits or quantum computers can only simulate unitary time evolutions. And the question is how to use these unitary quantum circuits to simulate non-unitary dynamics. And one idea is to use the dilation theorem, in which we introduce back some ancilla qubits or environment qubits that coupled with the system. And then you can evolve the system together as a whole object and trace out the ancilla qubits. And by doing that, we can arrive at a quantum circuit simulating the Lindblad equations. So in this quantum circuit, we introduce a bunch of number of ancilla qubits, they coupled with the subsystem, and they evolve according to this G operator here with a time step equal to square root of delta t. Like the G operator involves all the Lindblad operators that in the original Lindblad equations. And one can just work out the math and show that if you expand the evolutions to linear order in delta t, you can reproduce these Lindblad equations using this circuit. And then you can just repeat these cycles again and again. And in the end, you perform a measurement on your subsystem wave function. And we did some example studies. For example, we take a simple quantum two-level system. It just, there are only two states involved in the subsystem. Like we have you can think of a one state as an unbound Quarkonia state and a zero as a bound Quarkonia state. And this transition just describes the dissociation and recombination process I described earlier. And then we couple up this two-level quantum system with some scalar fields at a thermal equilibrium. And then we just use our kind of procedures to derive the Lindblad equations. And we have some Lindblad operators, and we can simulate these dynamics on a quantum computer. And here is the kind of detailed picture for the quantum circuit. Like symbolically, we write it this way, but in practice, you convert that into a bunch of single qubit and a 2-qubit gates, like the CNOT gate or some rotations along a certain axis. And then you try to kind of compile this circuit onto some real quantum computers, like the one provided by the IBM. And here are the kind of dynamical results we obtained from the IBM machine. And we're calculating the kind of ground state probability of the density matrix. We project the density matrix onto the ground state. And we start with a well-defined ground state. And then you can see like this ground state is decaying over time. This is just like the dissociation of a Quarkonian state. But there are several curves here that I need to explain. So first, it's the classical solutions, which is given by this dashed line here. This is the exact solution of the Lindblad equation. But in the quantum circuits, due to the limited depths of the circuit, we can only do one cycle in the quantum circuit. Like one cycle is just do this once. And then you can imagine as the time step becomes bigger, the truncation error becomes larger. This is why there is a deviation between the solid line and dashed line here. So for a good comparison to see the performance of the quantum computers, we need to compare the simulator curve, which is black solid line, with the dots. And there are three kinds of dots. The one dot is called uncorrected, and the other is called readout corrected, and the final one is called readout and rim corrected. The rim mitigates some CNOT errors. So it's a kind of a more advanced quantum error correction or quantum error mitigation. And you can see from these two dots, like they're labeled here, they are kind of deviate from this solid black curve here. But after we introduce this CNOT error mitigation, you can see the results are greatly improved. It has some reasonable agreement with the black solid curve. And this is really indicating in current kind of noisy intermediate scale quantum computers, doing error mitigation in a quantum simulation is very important. You cannot just do uncorrected calculation. That will just give you some nonsense results in the end. Yeah, this is our like simple demonstration for the kind of two-level systems resembling the Quarkonia dissociation recombination. Later, we did a more sophisticated model calculations, which is a gauge theory in 1+1 dimension. I just briefly go through the gauge theory in 1+1 dimension. Like this is the Lagrangian. We all know how to play with it. But to write down a Hamiltonian, we work in the axial gauge. We set A0 to be 0. And this is the Hamiltonian density. And then to put this Hamiltonian on a quantum computer, you need to discretize this Hamiltonian. And we follow the staggered fermion approach, which define another field chi with some gamma matrices multiplied by the direct fermion. And then we apply a Wigner transform, which maps the fermion field chi onto some spin systems like Pauli matrices, sigma, x, y, z. And then for the electric field and the gauge flux, we use a quantum ladder system. Like we just have some rising or lowering operators and the electric field playing the role as the eigenvalue of some state. And one can show these commutator relations for the gauge link and electric fields. And use this, we can kind of solve this gauge field in the original Hamiltonian. And after these procedures, we just arrived at a discretized Hamiltonian for the U1 gauge theory in 1+1D. It involves some Pauli matrices or hopping terms between different spin size. It also has some lowering and rising operators for the electric flux that are between these two spin size. And we also have some mass terms for the spin for the fermions, and also the the energy states for the electric flux. And then we couple this Schwinger model with some scalar fields again at a thermal equilibrium. We studied the Lindblad equations in the quantum Brownian motion limit. And here are some observables that we studied. Again, we did the quantum circuit on some IBM machines, and we compare it with the exact solutions. And now this time you can see that since we're using a better quantum computers, now we can do 4 cycles in the quantum circuit. And you can see clearly the simulator results, which is the black solid line, is closer to the classical results. That is because we increase the number of cycles. And you can imagine if we increase the number of cycles to be 10 or 50, then this black curve will almost be exactly the red curve. Okay. And for comparison, we also show the kind of vacuum solutions, which is just a von Neumann equation. There is no Lindblad operators in these dashed lines. This is the vacuum dynamics. And you can see the system does not summarize at all. But once we turn on the Lindblad operators, the system gradually approaches the thermal equilibrium, though it's not exact yet because of the limited number of cycles. And in this case, you see that the error mitigation still plays some role, but it's not that significant anymore. And the reason is just simply because the IBM machine we're using in this plot is much better than the one that I previously showed you. And it seems very possible that with better machines, we can extend this to a higher number of cycles and simulate the dynamics of thermalization of some quantum systems. But so far, it's still at its baby stage. We need better devices for sure, but we also need better algorithms to shorten the circuit depths, which can reduce significantly the noise in the circuit. Okay, now I reach to my conclusions. In this talk, I talk about the open quantum system approach for heavy quarkonia in heavy ion collisions. I show you how to derive the semi-classical transport equations in the quantum optical limit. Then I discuss some chromoelectric field correlators that matter for the Quarkonia dynamics. And clearly we see some difference from the correlators for the heavy quark diffusion. And then I discuss the quantum simulation of open quantum systems, where I show you some very simple examples at the baby stage. And for some future considerations, we would like to think about how to solve the real Lindblad equations for Quarkonia in the quantum Brownian motion limit by using quantum computers. And to do that in practice, you really need a very good algorithm to shorten the quantum circuit depths. Otherwise, the results will completely dominated by errors in the circuit or by noise. And finally, I show you a quantum simulation of U1 gauge theory in 1+1 dimension. Certainly, one would like to think about how to simulate non-abelian gauge theories in higher dimensions. I think this clearly is one future where quantum computers can be proven very useful in high energy physics. That's all. Thank you very much for your attention.
Thank you very much for a very nice talk. Okay, let me stop the recording first, and we can have some questions.